Now let us discuss that what happens to a particular nucleus. This should be nucleus, not nuclei. Nucleus is singular, nuclei is plural. What happens to a particular nucleus, suppose X, which emits an alpha particle? What will be its change in energy? What will be the change in momentum of this states? And of course, this alpha particle carries how much angular momentum? We should investigate those things. This is the energy axis. We have X, this is parent nucleus. We have the product nucleus as Y, and suppose it is a even nucleus. For even nucleus, the ground state should be 0 plus, and when alpha particle emits, another daughter nucleus is produced. This is also even nucleus, because alpha is 2, 4, Z equal to 2 and A equal to 4. Then the ground state of parent and product, both are 0 plus and 0 plus. Then what is the angular momentum carried away by alpha particle? Now, as the change of angular momentum between these two states are 0, because initially it's 0, finally it's 0. So, angular momentum carried away by this alpha particle should also be 0. There is another option, which is, let me tell you one thing, that this is the energetically lower state. The ground state of the daughter nucleus must be energetically lower than the ground state of the parent nucleus, because that is why nature does fission reaction. Nature does the emission of alpha particle in order to have better stability, in order to reach a lower energy state, that is this one. This is a higher energy state and this is a lower energy state. So nature always try to stay at a lower energy state. Now let's come back to another option where L equal to 2 amount of angular momentum is carried out by the alpha particle itself. If L equal to 2, that is the transition is between ground state 0 plus to 2 plus first excited state of this daughter nucleus, then change in angular momentum is 2. This L equal to 2 is carried out by this emerging alpha particle. From the collective model video, we have already shown that the energy correspond to the rotational spectra is L into L plus 1 H cross square by twice I. I is the moment of inertia, of course. L is the value of the angular momentum and H cross is H by 2 pi. This is a positive term because everything here is positive. L equal to 2, which is again a positive kind of thing. So we have a positive energy value here, and positive energy value is a manifestation of the repulsive energy. So this will add up to the Coulomb energy. That means the repulsion, the barrier faced by the alpha particle is something more than the Coulomb potential itself, because now this term is added to the Coulomb potential. So the alpha particle with some kinetic energy Q is now facing more a greater barrier height than the previous one, because this term is added to Vc. So is it possible to have this kind of transition? Yes, it is possible. But as the emission of alpha particle for this kind of transition is quite lower, so this will happen in a very few cases. 0 plus to 0 plus transition is the most favorable transition. Now what happens if the transition is between 0 plus to 2 minus? The first excited state is suppose 2 minus of Y nucleus. Is it possible for this transition to occur? The answer is no. Because if if the angular momentum change is 2 unit, we know parity is positive then, because parity is defined as minus 1 whole to the power L. L is 2, so parity change is positive here. So L, this is a 2 minus state, a negative parity state. So this transition is a forbidden one. 0 plus to 2 plus is okay with a fewer probability. 0 plus to 0 plus is more favorable for the alpha particle.